to draw a galvanic cell and an electrolytic cell. For the galvanic, let's do tin. And I'm not going to do states because I'm cool that way. And we'll do iron. So in a galvanic cell, we're looking for a backwards Z. So this way and this way. There's the cell bridge, KNO3. And we'll make this the tin half cell. That's Sn solid, and that's Sn2 plus aqueous. And then because both the reactant and the product are aqueous, we use an inert electrode like carbon, graphite. This is the anode, and it's negative. This is the cathode. It's the cathode because C stands for cathode. And the electrons go this way. Because tin here is losing electrons, and iron is gaining electrons. So they go from the tin to the iron. As tin loses electrons, more Sn2 plus enter. So to balance out the charge, the NO3 minus will go into this half cell. And when Fe3 plus reduces to Fe2 plus, the charge will decrease, the positive charge will decrease, so more positive potassium ions will enter. And it's reactant product, that's the anode, and that's the cathode. So we will write this out as reactant, Sn solid, product, Sn2 plus aqueous, salt bridge, reactant, Fe3 plus aqueous, product, Fe2 plus aqueous. It's beautiful. Now we're going to do electrolytic to the same cell. Okay, so this is the electrolytic cell. We'll use the same iron and tin because it's cool. And so in electrolytic cells, it's actually a correct way Z. So it's going this way. Have a cell bridge as usual. There's our electrodes. Complete the circuit. It's done. We'll make this the tin side. And we'll make this the iron 3 plus, iron 2 plus. And we'll use carbon again. So now we have a load that is forcing electrons this way. So the Sn is gaining electrons and reducing, so it's the cathode. the Fe2 plus is having its electrons taken away, and so it's oxidizing, and it's the anode. And because electrons are being forced into this electrode, it's going to be very negative. And because the electrons are being taken out of this, it will be positive. There you have it. I drew 4 half cells. I drew 2 full cells. Okay. I forgot about the cell bridge. Schoolboy error. Okay, so this side, the Fe2 plus is turning into Fe3 plus, and it's getting more positive. So we want the negative KNO3 to balance out the charge. And on this side, the SN2 plus is turning into SN, and it's becoming less positive. So we want the positive potassium ions to balance it out on this side. Okay, so I found a pretty cool question. It goes like this. There's a graphite electrode. Man, I love graphite. And it's in an aqueous solution of CuNO3, 2, AgNO3, and KNO3, all 0.100 molar. And after a while, it develops 3 coatings. Those are 3 coatings. So it's electrolysis. So is it the anode or is it the cathode? See, it's got things turning into solids on it, like Cu2 plus turning into Cu, or Ag plus becoming Ag, or K plus becoming K. And if you add the electrons, you discover that these are reductions. And if it's reducing, it must be the cathode. See the C here? It stands for cathode. Okay. And now the question is, which layer is which? For this question, we will need the electrochemical series. So Ag comes first, and then it's copper, and then it's K, potassium. Now potassium here wants its electrons the least. It does not want electrons at all. So when you're pumping this electrode full of electrons, potassium's going to be like, I don't want any. But silver here, which wants its electrons more, will take the electrons first, because it's the highest here. On this table, it is the weakest reductant and the strongest oxidant. It wants electrons the most. So it will be the first to take electrons and turn into a solid. So coat 1 is silver. And out of copper and potassium. The one that wants its electrons more is copper. So code 2 is copper, and code 3 is potassium. Now this doesn't happen in real life, because if copper solid formed in an aqueous solution, it will just explode. Anyway,